Okay, let's go for the next lecture. This lecture is gonna be on moment of inertia. From the beginning, let's try to define some concept, right? Inertia, we can define it as the resistance of an object to change its velocity. We can define mass in relation to inertia, right? How much inertia an object has, right? The more massive is the object, the more is the resistance to change its velocity, right? In this way, we relate mass and inertia. Now let's go to moment. Moment is defined as the product of a quantity and a distance. Remember, a quantity, we have two groups of quantities in physics, scalars or vectors, and then we multiply those quantities and the distance and we create the moment. Moment of inertia is coming from rotational conditions. When we're dealing with inertia at the beginning, right, we work with motion in 1D, right? In a straight line, for example, we have this object, right? At the beginning is a rest. This rest is zero. What happens when we apply a force? When we apply a force, we change its velocity, right? So we create an acceleration. So if we increase the mass, of course, the resistance is more of the object in changing its velocity, correct? But what happens in the rotational cases? In rotational cases, the same thing, right? We have an object, we want to make it rotate. It also has resistance to be rotated, right? But the resistance doesn't depend only on the force. It depends only on the position of the force respect to the axis of rotation, correct? And we call that, again, when we're dealing with rotation, moment of inertia. Let's try to get that condition. Imagine that we have kinetic energy. Remember, kinetic energy is equals to 1/2 mv squared, right? Now let's go to rotational conditions. Okay, let's go to rotational conditions. So what do we have? Remember, we have V is equals to R times omega. Great. Now let's involve this quantity right here. And what do we have? We have 1/2 m mass times V squared, but V now is this amount, right? R omega squared, right? Now what do we have? It's equals to 1/2 m R squared omega squared. We call this, right, the rotational kinetic energy, right? Rotational kinetic energy is defined then as 1/2, right, m r squared times omega squared. Now this quantity relates mass and distance, right? Which is coming from this product, right? For this definition, product of a quantity and the distance. Quantity and the distance give us momentum. Momentum of what? Momentum of mass of inertia, correct? So then we define this product, right, m r squared as the moment of inertia, correct? This is the moment of inertia. Now, when we go back to the initial equation, we get that rotational energy is equals to 1/2 moment of inertia omega squared, right? This is the origin, right, for this quantity moment of inertia. Okay, now let's apply the moment of inertia for some object. Could be singular object, particular object, or could be solid. Okay, let's do it. For example, imagine that we have a particle, right? We have a particle moving right along this axis of rotation. The distance r, right? And this is the mass. So we rotate in that way. How we can find the moment of inertia? Well, we just did it, right? Moment of inertia, right, is equals to the product of mass, right, times the distance to the axis of rotation squared. Right, so it's gonna be the moment of inertia for this particle. What about if we have a bunch of particles, right? So when we have many particles, let's go to the summation rate of this m sub I r sub I square. Correct? They have the same form. Now, what happens if we have a ring, right? Imagine that this object is moving very fast. This mass is moving very fast. When this mass moves very fast, right, it creates kind of a ring, right? We don't see the mass, we see a ring, right? Means what? That the moment of inertia of the ring must be equal to the moment of inertia of a single mass. Okay, let's do it. Let's do it this way. Okay, imagine it's a ring, right? Now this is the ring right here, correct? This is the axis of rotation, right? The mass, well, this is the ring right here. That's the ring, correct? And right, it rotates. Now, let's go in this way. Let me erase this part. We found that moment of inertia in general, right, for particles equals to the summation m sub I r sub I square. Now, when we're dealing with a solid, right, the formula, right, becomes in this way: r squared times dm. This is for solids. Okay, this is a solid. Let's do it. Imagine this is the ring right here. This is the ring, correct? And it rotates, right? And we're looking for the resistance, right, for this ring to be rotated. And we call that the inertia, or moment of inertia. Okay, let's do it. Let's take a segment right here, because we're looking for an element of mass. Okay, let's take this element of mass, right, my dm, and it takes, right, this angle, because it's a small one. This angle is going to be d theta. The radius, right, is constant. Also, remember, we know that this arc length is gonna be infinitesimal 1, 2, but we define the arc length as r right times theta. Correct? Now, taking this into account, let's go to the formula, okay, for solid. Let's do it. Let's do it. So we have that moment of inertia for a ring is going to be equals to the integral, right, r squared, correct, dm. But what is dm? Dm, when we're dealing with solids, right, in these cases, we used to work with densities, right? And we have these three types of densities. We have linear density, right? Usually we use lambda equals to mass over the length. We have surface, right, or area, right, density. The same way, let's use sigma equals to mass over area. And we have the volume density. Usually we use a rho equals to mass over volume. Okay, let's try to find the moment of inertia for three different objects. One using linear density, another one using surface density, and another one using volume density. Okay, let's do it. In this case, we are with linear density. Perfect. We are with linear density. Okay, so in this case, we use lambda equals to mass, right, over L, right, because lambda is constant, and right here we're dealing with an infinitesimal mass. So also we can say that this mass divided by this, we can call it L, or we can call it X, right, in 1D X, or in this case we can call it S, right? That's the length from here to here, right? Element of length, right, is gonna be S, correct? Now from here we can solve for dm. dm is the total mass over L times ds, correct? Okay, and then we plug this value right here, right? Okay, now let's do it. So do we have moment of inertia is equals to the integral r squared m over L, right, ds. Perfect. But where is ds in function of, let's see if we can find a relationship between ds and r, or just ds. Let's see what happens from this condition right here. So what do we have if we take the derivative of ds, where r is constant, stays the same, is gonna be r d theta, correct? Now what happens if we substitute this value right here? Let's do it. So it's equals to the integral, right, of this r is the same as this r. Okay, right here it's gonna be r squared, right, ml, right, times r, right, d theta. Right, correct. Now let's continue right here, right, and we have that moment of inertia is equals to m, right, r cubed, correct, over l, correct, times the integral of d theta. Right, now d theta, or theta, goes from 0 to 2 pi, right, from 0 to 2 pi. When we do that integral, what do we have? So this is equals to mass r cubed, right, over, or we can use this r right here. You want to write this r, okay, we can use this r, okay, this r just to match this r right here, okay, r, perfect, okay, it's constant, it's gonna be constant right here, okay, times over l times what, 2 pi, correct? Okay, now but what is l? What is the total length? The total length, right, of the this ring is equals to 2 pi r, correct? Now, when we substitute this value right here, what do we have? It's equals to m r cubed over 2 pi r, correct? Divided by, or times 2 pi, correct? So this is equals to m, right, r squared, which was the same, right, which is the same as the momentum for one particle, right? Perfect. So we found then the moment of inertia for the ring. One more time, moment of inertia through the center of mass of the ring. It's very important, right? It's equals to mass times r squared. Okay, let's go for a plane, a surface. Okay, let's go for a surface. When we have a surface like a disc, okay, imagine that we have a disc right here, right, disc, the same thing. Let's look for the moment of inertia. Right, now for this one, let's take a surface element of area like this one, right, around the x rotation. This is the element of surface or element of area, this one, correct? Or also we can say the element of mass. Okay, this is my element of mass, my dm, because in the equation we're looking for dm. Okay, perfect. Now let's do it right here. Let's do it right here and see what happens. So we have that the moment of inertia for a disk is equals to the same formula, integral r squared, right, dm. Right here we can differentiate, right, between two radius. This is one radius and this is another radius, right, r, correct? And now the thickness for this element, right, is equals to dr, correct? And now we continue right here. Let's see what happens. It's equals to r squared. What should be dm? The same thing as before, right? Remember, we have now sigma, the surface density, is equals to mass over area, correct? Mass over area. And then we can also make it equals to dm over dA. But what is the area of this segment, right? Well, this is this segment right here, right? We just cut it and make it straight, right? And we create a rectangle. This side is the r, and the length is gonna be the circumference, which is 2 pi r. Now, what should be this area? This area is my dA, right? dA, the element of area, right, equals to this product, right? 2 pi r dr. Correct? Now we apply this equality right here, right? And this equals to r squared times 2 pi, right, r dr. And then r goes from where to where? From 0 to r. right? These are the limits from 0 to big R. Perfect. And now this equals to what? 2 pi integral 0 from 0 to R, right? R cubed dr. Right? Perfect. And now this is equals to 2 pi. What is this integral? It's R cubed over 3, right? From 0 to R, right? And we do this calculation in this way, correct? So this is equals then to 2 pi. I forgot something right here. It looks like something is missing for the A. Look right here. Look at the end. You look here. I remember for the M. The M is equals to M over area times the A. Correct. So I'm missing right here. Right, M over area, mass over area. Right, the same thing right here. Right, mass over area. Perfect. Okay, mass over area. Okay, great. And one more time, this is gonna be 2 pi mass over area, correct? Correct, oops, correct, times R what? R cubed, this is gonna be 3 right here, right? R to the 4th, right? To the 4th power. Okay, perfect. Now, let's try to substitute the value for area, right? What is the area of a circle? Remember, the area of a circle is equals to pi r squared, correct? Now let's do it. In this case. Actually, look, the integral is divided by 4. Sorry, it's gonna be this divided. It's gonna be r cubed. It's gonna be r4 divided by 4. Correct. Perfect. And then there's gonna be what? Perfect. This is gonna be 4 instead of 3. Okay, great. So this is equals then, when we substitute this value, it's gonna be 2 pi m r to the 4 divided by 4 pi right r squared. Correct. And this is equals to what? Mass r squared divided by 2. Okay, and that's the moment of inertia for the disk, right? For a disk, right? Moment of inertia we found, right, from this analysis. Moment of inertia is equals to m r squared divided by 2. Right? It's for this. What about for the ring? Remember, for the ring is equals to m r squared. Right? Who is represent more resistance? The ring. Why the ring and not the disk? Because most of the mass is farther to the axis of rotation than for the disk. Here we have the same mass, of course. Got it? Okay, perfect. Now, what about for a volume? Let's say a cylinder or the sphere. Right? Look, we mentioned that if we have an object, right, that moves very fast, we have an object where we have a moment of inertia for this particle. This particle moves very fast. Now, produces kind of a ring, so the ring and the particles, right, have the same moment of inertia. What about for a disk? The disk, the disk right here, we can rotate in this way and we can create a cylinder. So the ring and the cylinder, right, have the same moment of inertia. The same thing as a particle in the ring, right, happens to the disk and the cylinder. Because you can see right here, we see just a disk, but when you rotate a little bit, you can see actually it's a cylinder. So both, right, present the same moment of inertia. We found the moment of inertia for the ring, right, for the disk. Now let's do it for the cylinder. Okay, let's do it. For the cylinder, right, again, let's take this cylinder right here, right, let's take the axis of rotation through its central mass. These are through the central mass, okay, central mass, perfect. This is the central mass of the cylinder, correct. The same thing as for the disk. Let's create, right, a infinitesimal cylinder inside, right, like this, right? Perfect, as we did for the disk, right? And this is my dm. Remember, one more time, we need to apply this equation, right? R squared dm, and we're looking from the beginning for my dm, right? This element of mass. Perfect. Let's do it right here. So this is the element of area. We just found it before, right? And we found that this dA is equals to, remember, it's gonna be 2 pi r dr. We just found it. Okay, from the previous, it's right here, right? It's right here. It's the same this at the top, right? Now let's go to the volume density, right? Volume density is equals to mass over volume, right? Or now we can use this element of masses in this way, the m over, right, the volume, element of volume. Okay, now let's go for the volume is equals to what is the volume of a cylinder? Remember, volume of a cylinder, volume is equals to the area of the base, which is, right, A times, let's say, height, h, times h, correct? Now h is constant, we're changing only, right, this area right here, and we have this is h, right, dA. But dA we found is this one, so this equals to 2 pi h, right, r dr. R dr. That should be the element. R dr. Perfect. R dr. Correct? Okay, great. We can substitute this value right here when we solve for dm. Now dm becomes, right, equals to m over volume. Correct? No, f of m over volume times dv. Right? Where dv now is this quantity right here. Perfect. Let me continue right here. Great. So what do we have? We have the moment of inertia, right, for the cylinder is equals to the integral r squared, right, dm, but now dm is equals to mass over volume times dv, right, which is 2 pi hr, correct, dr. Right, and this equals to, what should be the limit, right, for r. This is again r, one more time. This is my big R, this is little r, and this is the element. We did the same thing as for the disk, right? So my dr, the same thing. Okay, perfect. Now this is gonna be the limit from 0 to big R, right? Of what? Let me do it this way better, right? Usually the constant goes at the beginning, right? Gonna be 2 pi, right? What? H m over v times the integral from 0 to r, right? Of what? R cubed dr. Correct? Perfect. Now let's continue. Where I need more room. Oh my god, this board is so small. Okay. Let me do it right here. Let me continue right here. Correct. So moment of inertia then is equals to, okay, 2 pi, right, h m over v, right, integral, right. Well, let's do the integral right now from here, right, and we have that this is equals to, right, r to the 4th over 4th as before, right? Okay, perfect. Okay, and we have that equation. Perfect. Now let's go to the volume. We found volume right here is area, right, times h. But what is area? Area is equals to pi, right, r squared times h. Okay, let's do it. So it's equals to what? It's equals to 2 pi h m, right, over volume, which is pi, right, r squared times h times r to the 4th divided by 4. Correct? So as you can see from here, this is equals to m, right, r squared divided by 2. which is the same as for the disk. So the moment of inertia through the center of mass of a cylinder, right, is equals to mr squared divided by 2, which is the same as for the disk. Correct? Okay, perfect. Now, again, we cover the moment of inertia for this object. We have one more, an easy one. Let's go for another one, right? Imagine that we have this rod. Imagine that we have this rod right here. Okay, this one, okay. And we have to rotate it through the center of mass. This center of mass, right? The length of this rod is L, right? Now, because it's a solid, right, we use the integral moment of inertia equals to the integral r squared times dm. Again, we take an element of mass, right? This is an element of mass right here. Because of the formula, this is my element of mass. So my dm. Now look, this element of mass is rotating, right? It's rotating. So it needs the radius. So what is the radius? Let's say this one, let's call it x. Imagine this is my x direction. That's the radius for this element of mass, right? Which is rotating, correct? Perfect. And because we're dealing with density, right? Linear density is equals to mass over L is equals to dm over the element of length. In this case, dx. So we need also to represent the dx. In this case, what should be dx? Well, it's gonna be this thickness, right? dx. Now we have all the quantities. We have the element of mass, we have the distance from the x of rotation, what we call it x, right? Or the radius, in this case, gonna be x, correct? And because we're dealing with densities, right? We need the thickness, right, of that element of length, right? And we call it dx. So we represent all these quantities right here. We need all of them again because this is the original idea, right? We have a particle, any particle moving, right, on respect to one x of rotation. This particle, we need a radius, right? When it's particle, it's okay, but when it's a solid, we need densities. And that's why we need also to add an extra quantity, right? In this case, the element of length. Later, we need the element of area, of the element of volume, depends, correct? Okay, let's do it. So let's go back then to this case. So from here, we have that the moment of inertia, right, is equals to r squared dm. What should be dm from this equation? We have that dm is equals to the torque mass over L, right, times dx, correct? For simplicity, let's match this dx with this quantity, so we can call this x, right, square times what? dm right here, correct, is equals to m over L, correct, times dx. Okay, perfect. Now let's see the limit. The limit right here is L over 2, and right here is L over 2 negative respect to this x of rotation, the origin. Okay, perfect. Now these are the limit from negative L divided by 2 to L divided by 2. Great. Now let's do the integral. So from here, moment of inertia is equals to, right, m over L, right, times times the integral, correct, of x squared dx, right, from L over 2 to L over 2. Perfect. And what is this? This is equals to m over L times x, right, cubed over 4, correct? Over 3, right? Over 3. Perfect. From where to where? From negative L divided by 2 to L divided by 2. Right? Perfect. And this is equals to, let me do it right here, let me continue right here, equals to what? M over L, right? 3L actually, correct? Times what? times L over 2, right, cubed, minus negative L over 2, right, cubed. Perfect. When you do this calculation, this is equals to mLq over cubed over 12L. Correct? At the end, right, this L cancels one with this L, and what do we have? Moment of inertia, right, for this rod to the center of mass, through the center of mass, equals to m, right, L squared divided by 12. Correct? And again, that's the way how we calculate the moment of inertia for solid. Okay, now let's go to, let me see if we have time. Let's go to see the perpendicular axis theorem and the parallel axis theorem. Okay, I see you in a moment.